All right, so where we last left off was epoxides, right? I think we just did preparation reactions or like synthesis of epoxides. So today, just to finish up chapter 13, we're just gonna do questions that reactions of epoxides, right? So like if you have an epoxide as your starting material, what kind of products you can get out of it. And there's essentially two types of conditions you could put epoxides under, either under strong nucleophilic or basic conditions, if you want to think of it like that, or acidic conditions, right? And the product you get kind of differs depending on those conditions, right? But it's kind of easy to generalize it. I think your book kind of does it in the back of the chapter pretty well, but there's a couple of things it doesn't really mention. So we'll just go over that. So let's start. Oh, just choose a little better color. Use white. Hopefully better contrast than the black background. Okay, so let's start with 13.16, right? Start with a simple one. Let's start with A, right? So we have an epoxide here, right? And this is a methyl group. And you have a, what kind of reagent is that? Grignard, right? Gryffindor. Okay, so a Grignard, right, is a strong nucleophile. Essentially, you could think of a Grignard as a carbon nucleophile, right? So we're under strong nucleophilic conditions, right? Which means what type of reaction pathway do we expect with a strong nucleophile and epoxide? SN1, SN2, E1, E2, SNAR, SN2, right? So whenever you have a strong nucleophile, it's going to want to go through a SN2 concerted mechanism, right? And in this case, you have a good enough electrophile, which will be your epoxide, right? So the really only thing you need to understand is when you have epoxides, right, it's always going to attack the least hindered position, right? So in this case, you get, I guess you could call this kind of a tertiary position, and this would be secondary or primary, however you want to look at it, right? So basically the position of the epoxide with less groups on it, right? And then it breaks open the epoxide, and then you're gonna get your final product, which is usually always an alcohol, right? With whatever group you attach to it, right? And this question asks you to predict the product and draw mechanisms, so we will do both, right? So with the Grignard, there's a couple of ways you could do the reaction mechanism. They're all accepted, right? I generally like to do it like this, where I grab my electrons from the carbon magnesium bond. You could also draw it like this. Some people just like drawing it as the carbon ion. That should be okay too, right? But generally I like drawing it from the bond, right? So this attacks there, right? That carbon, right? If you want, you could probably draw it from the carbon too, but the carbon metal bond essentially indicates these are electrons that are on the carbon, and those are what are attacking this electrophile, right? So this kicks open, right? So never forget your arrow. So that's your SN2 mechanism right there, right? It attacked, it kicked open. It's all on, except when it kicks open, it's still going to remain on the molecule, right? So now we move forward. And you're going to get, let's try to draw this properly. Should be a methyl group, right? This is going to be your pH group, right? Draw the ring if you want to. Doesn't really matter. And then this will be O minus, right? And then the second step is the workup step, right? We turn the, I guess you could call this an alkoxide into a alcohol, right? So second step is pretty straightforward. Grabs a proton. Remember, we're only grabbing a proton, so the electrons have to go back to whatever acid you're grabbing the proton from. In this case, it's water, right? Final product. So that's a good question, right? Let me just draw out this product, right? So was that Hamad asked why the O is on the right? Could it be on the left, right? So essentially you're asking how come we don't get this product? Oops. Like this, right? OH. This would just be a methyl group. Right. So when you break open the epoxide, right? Let's go back to that first step, right? The bond that is breaking is on the side where the nucleophile is attacking, right? It's not going to break the other bond when it attacks, right? Because this carbon, right, technically has 4 bonds, right? So this oxygen is breaking that bond between that carbon and oxygen, right? So, I mean, it's a good question because some people, when they're doing it quickly on your exam or something, you might mess up and draw the OH on the wrong position. So it's a good thing to always remember that when you're under strong nucleophilic conditions, your OH is not going to be on the same side as your nucleophile, right? It's going to be ending up on the opposite side, right? So once again, to repeat, right, is in this first step, let's circle it, right? Here, circled in blue, right? When your nucleophile is attacking the epoxide, right? What's not shown here, right? So we should all be comfortable with bond lines at this point, right? The oxygen, this carbon has 4 bonds, so it's being attacked, right? Now it's getting another bond, and at the same time, right, one of its bonds is breaking, and that's the bond between the carbon and oxygen, right? So that O cannot be attached to the same carbon your nucleophile is attacking, right? Because then otherwise you'd have 5 bonds on there. And this bond, it would make no sense for, let me just circle it, this red bond, it would make no sense for that red bond to break because you're not doing anything at that carbon causing this bond to break, right? So the only bond that will break is on the same side as the nucleophile, right? Because it's just a classic SN2 mechanism. Okay, let's try another one. See if any of these structures are a little different. Okay, that's a good question too. So the reason we wouldn't attack from an ME side, right, is has to do with the I guess selectivity of regio. Oh no, that's I should have saying regio selectivity. That does have nothing. Well, I mean technically it is regio selectivity, but it has to do with the selectivity of the nucleophile, right? And that's in 2 reactions, right? If you remember, what is it? If you have something like tertiary Cl or Cl layer or something like this, right? Essentially, you'll see this is the best for SN2, right? And that's because the leaving group, it has as Nada said there, it's the least sterically hindered position, right? So when your nucleophile is coming to attack, right? Remember, if you think of these instead of just like, paper and pen drawings, right? Think of them as clouds of electron density, right? This area, let's circle with red again, right? This area has a lot more electron density, it has a methyl group, and it has that whole epoxide. It's going to be harder for the nucleophile to come in there and attach itself, right? It's going to be a lot easier to access this green area, right? Because there's only hydrogens in the way there. There are a lot less electron density, right? So sterically, the less hindered position is more accessible, right? And that's why it attacks the least hindered sides, because those are just the outcomes of SN2, strong nucleophile pathways. So when a hydrogen proton catalyst is involved, we would be, well, that depends, right? So like I said, when we do the acid catalyzed stuff, there's going to be a couple of things that play. There's steric effects, and then there's also electronic effects, right? So we'll cover both of those. So let's do another one with strong nucleophiles. But hopefully everyone's good on why, right? It's attacking the least hindered position, right? That just has to do with SN2 mechanism pathways, right? To put it very simply, it's a steric hindrance. Okay, and also remember, the stereochemistry was conserved at this carbon here, right? And that's the thing to remember, right? Because all we did was we didn't really do any chemistry at that carbon, right? So stereochemistry is still isn't also because the carbon. Well, technically both carbons of a epoxide are electrophilic, right? Then it's depending on the reaction conditions and any other R groups attach, which one becomes more electrophilic, right? Under certain conditions, you'll see maybe a tertiary position is a better electrophile, right? Because of electronic effects. And in certain conditions, you'll see the secondary position is more electrophilic because of steric effects, right? But technically, right, the dipole is going this way, right? So these are both technically partially positive, right? Serichem is the methyl would just be drawn with dashed. Um, what do you mean by dash? It's gonna stay on its wedge, right? Because we didn't do any chemistry there, right? So in this case, the methyl is on a wedge in the original starting product, and it would be on a wedge. Oh, if you mean if it was like on a what's it called? Like where the nucleophile was being attacked. Oh yeah, then there's inversion of configuration, right? Though I haven't really seen examples of that in what's it called? Epoxides, but technically any SN2 reaction, right? If you attack at a position, right, you would have inversion of configuration, right? And you could show that by showing the like a R group going from a wedge to dash instead of the other groups, right? Let's see which one. Okay, let's do E and F. Oops, wrong color. I'll let you guys try these. Take like 3-4 minutes to try these since you have to draw out the mechanism as well. I'm gonna abbreviate the group. I mean, if for those who have the textbook open while we're doing this recitation, like that's why I write the numbers and letters. So like you could get started a little faster, but sometimes I abbreviate structures. So in this case, I'm abbreviating that phenyl group. Here it's ET. And then your reagents are sodium ethoxide and water. That's one. I'll write the other one later and then move it down once we get to it. And this one is oh right, kind of need the stuff that's attacking it. Okay. The SN1 example, yeah, when we get to, I guess, well, I mean, technically it's not really SN1, the acid catalyzed. It's still kind of SN2 if you think about it. All you're kind of doing is you're just protonating it to make a so essentially what's happening, right, is while you guys work on this, and let me just briefly explain, let me zoom out so that way the questions are still in view, right? It's not SN1 when you're dealing with epoxide. It's both ways it's SN2. Essentially what you're doing is you're kind of changing the nature of the electrophile. So in a strong nucleophile reaction, the name kind of gives it away. You have a strong nucleophile, right? So the electronic kind of interaction that happens all has to do with the, I guess, if you want to think about it, the HOMO of the nucleophile, right? The nucleophile is very electron rich, right? And it's going to usually have a strong negative charge, right? So you don't need a very strong electrophile because the nucleophile will go hunting for anything partially positive. So that's generally the case when you have strong nucleophiles with full-on charges and good homos, right? And then the epoxide you don't really need to do anything to the epoxide, right? And that's why, all these reactions, it works out the way it does, right? Because the nucleophile is essentially providing the electron density. Now, what happens when you want to use nucleophiles that are kind of moderate or weak, right? This is where acid catalyzed stuff comes into play, right? Now, the difference is kind of this reaction is more electrophilic in nature, right? The first one was all dependent on the nucleophile because it's very strong. And this one, what you're essentially doing is increasing the strength of the electrophile, right? When you put it in their acid catalyzed conditions, right, you usually get something like this. It's going to be a plus charge, right? Which means this is, oxygen, right? Wants its electron density. So these carbons, you could kind of consider them more electrophilic than in this case. If you put this as a partial positive, we could think of these as partial plus plus, right? Because now you added a proton here, you protonated it, right? Oxygen lost some electron density, right? And it's taking that electron density away from the carbons. So the difference in the nature of these reactions is that you're making this electrophile stronger. The first one, you have a strong nucleophile. Second one, you have a strong electrophile. But then the second process is still the same. Whatever nucleophile comes in, let's say like, I don't know, water, right? Water will come in, it's a moderate nucleophile, right? But now you have a much stronger electrophile. So that causes the attraction, right? And it's still an SN2 process though, right? So it's never SN1, right? All you're doing is changing the nature of the reaction, whether it's inherently a nucleophilic reaction or it's an electrophilic reaction, right? So don't ever draw an SN1 mechanism, I guess, for the epoxides, because that's not going to be happening. It's kind of just the order of when the SN2 step happens, right? And this, technically the oxygen is protonated first, right? Okay, so let's go over these. I think should have enough space. Okay, so here we have OET minus, right? So we could just represent sodium ethoxide as this, right? Because it's technically a salt of Na plus and OET minus. Goes attacks the less sterically hindered position, breaks open, right? Go down here. Now we could draw minus pH ET OET. Remember, it's the O that bonded here, right? So technically, we also made an ether here and an alcohol, right? So now we have OET. Next step is going to be just simply work up. Oops. Okay, so hopefully everyone got that. Anyone get anything different, or we're all good on that answer? Okay. Remember, the stereochemistry is still preserved, right? Here, here, and here, right? Those groups are still on the same wedge scissor dashes, right? Now the second question, I guess we didn't have to bring it down that little. Right? We have lithium aluminum hydride, right? And that is a source of nucleophilic hydride, right? So as I mentioned in the first recitation, right, we had NaH and we had LaH4 or NaBH4, right? NaH is a source of basic hydride, right? There's no polarizability, so it only acts as a base. Sodium borohydride or lithium aluminum hydride, they have a BH or ALH bond, which has some sort of polarizability between the Al and the hydrogen, which allows the hydrogen to act as a nucleophile, right? So for simplicity's sake, actually, you know what? I'll just draw it all out, just so in case that's what's asked for you on your exam. So sometimes I'll just use H minus, right? Because technically we call this a delivery agent of a nucleophilic H minus, but the proper way to, I guess, do it is like we did the Grignard, right? To show the hydrogen is coming from the metal hydrogen bond in this case. So, you know what? Make this even easier. Write it like this. Okay. So once again, you have a, I guess we could call this quaternary center, right? This has 1, 2, 3, 4 groups, and this has only 3 groups, right? So the only position it can attack is this one, right? It can attack, just to be clear, it can never attack at this position, right? The reason being is that it already has 4 bonds, right? So if you attacked here, this would be too sterically hindered to do it. But it can at the methyl group, right? Actually, I have to check. Maybe there is some literature where you could attack it at that kind of quaternary or tertiary position. But for the most part, you'll never see attacks happen at those kind of positions. Okay, so let's draw the electrons. Goes here. Yeah, so it's going right there. Maybe let me draw that arrow a little better. Right, so it's attacking that carbon. It breaks open this bond, right? And now we get our first intermediate, which is similar to that last product we drew, right? And oh, sorry, I started skipping steps. Thank you. Yeah, that's the next step. Next step is going to be workup, right? Okay. And final product going to be this is pH, and this should be ET, right? So I'm glad someone asked the question of why the methyl is no longer on a wedge, right? So what was our nucleophile in this case? It was H minus, right? At this point right now, right? So this is why choice of nucleophile is very important, right? At this point right now, right? This is a stereocenter. You have a methyl group, then you have a carbon attached to carbons which are attached to other carbons. You have a carbon attached to, you have an oxygen, and then you have, it's not shown, it's a hydrogen, right? So what we added here now is a hydrogen, right? So at this position now, here, right, what's not shown, but that was already there, was that other hydrogen. And boom, you automatically lost stereochemistry there, right? Because you have two identical groups on the carbon, right? And that's why there's no dash or wedge, because you lost chirality at that carbon, right? So choice of nucleophile is important, right? So if I like, same thing, like if you attach something like, let's just do a side example here, right? So if we did the same thing, boom, and this, right? So if we use something like a methyl Grignard, right? So CH3 MgBr, right? It would also lose its stereochemistry, right? Because now two groups that are similar are the methyl groups, right? But if we use something like, I don't know, let's use sodium methoxide, right? Now it will still keep its stereochemistry. It will just be inverted, right? Because now you're attaching a fourth distinct group, right? So just make sure you're aware of what nucleophile you're using. In this case, the question used LAH, right, which was attaching a hydrogen to it, right? And because there was already a hydrogen present at that carbon, right, we are essentially destroying the chirality at that carbon, right? Which is why in the further structures, I didn't draw any wedges or dashes, right? You just have to be aware of that. So if you use any nucleophile that adds a similar group, so the only two cases you could do is basically in this specific example would be hydrogen or a methyl Grignard, right? You would lose chirality in that molecule, right? Here you would get a final product that looked like this. Sorry about that. So this would be your final product here. And then here, right, you would actually have inverted configuration. So what did we attach here? OET. So we could represent this methyl like this, right? So this was that case I was talking about, in case you ever or somebody asked before about like someone asked about the inversion or whatever. But there's that case, right? So if you did have the SN2 reaction, in this case, the methyl would be on a dash instead, right? But it just happened we used a hydrogen nucleophile, right? So always be very careful of what nucleophile you're using and stuff, right? Because if you're using something that attaches the same group, right, you're destroying chirality, right? Which may or may not be useful in terms of synthesis, right? Maybe there, some sort of potential drug candidate you're creating that, you need to lose chirality at one carbon for whatever reason. You could do it this way, or not this way. This could only work for epoxides, but preserving, inverting, and destroying chirality are very important things in synthesis, right? Can you scroll up to E? Yep. Okay, then we're gonna do acid catalyzed, and then we're done for chapter 13. Right. For those that are here from boson, we're not gonna really be doing the sulfur stuff. But I think that's the only thing in terms of both their syllabuses that that's slightly different. But everything else, I'm pretty sure whatever Biscoe covers, boson covers, right? But the sulfur stuff is very, very simple. If you really want, you could probably find me briefly talking about it in an old recitation. I'll try to find which specific recording and then mention it. Okay, so hopefully you're good on E. Okay. Let's do acid catalyzed, right? So these reactions were all epoxide reactions that were nucleophilic in nature, right? Essentially, the main exploit was using a strong nucleophile. Now, when we don't have that, we use a strong we increase the strength of the electrophile, right? It's a little kind of ways we cheat, right? Sure. Actually, while I do that, actually, let me zoom it out so you could see both. And let me look for questions. Where is it? 13.18. Okay. And which one? E? If you're talking about E, as Dominic said there, it's not chiral at all, right? It has 2 hydrogens already, right? So adding a third group is not going to change whether it's chiral or not. The example you gave, yeah, no. So I drew it as oh, this one, right? This is what you're talking about. Yeah, no, I just like showed the inversion of configuration by just switching which side the methyl was on, right? So the methyl originally here is on a wedge, right? So you could show inversion a couple of ways, right? You know, if I decided to draw this on a wedge or whatever, but an easy way of usually showing it is whatever R group that's showing stereochemistry, just flip the sign. Flip the wedge to dash or dash to wedge, right? So that's what I did, right? And that's indicating that the methyl is on the same side as the phenyl now, and that's because of the SN2 attack. Okay, let's do 13.18 now. So now we're doing more electrophilic reactions, right? And remember the first thing I said in the last recitation? Yeah, Madrona, what's up?
So can we just say that, is it okay to use my mic?
You guys are free to, you know,
Okay.
ask questions with your mics or whatever. It's not like you have to use the chat.
Okay, so so the difference between bases and acids in terms of ring opening reactions is that in bases we do the SN2 and then we do the proton transfer, and then in the acids we do the proton transfer and then we do the SN2.
Okay. While you type your question, I'm just going to start writing. So I'll still answer your question. Just want to make sure I start writing. Okay. Okay, let's not do A. Let's start with B. E, H, B, R. Okay, I don't know what your question's gonna be, Madrona, but I'm gonna start this problem, so I'll answer it later or just post it in the chat or whatever. Anyways, so now we're doing the acid catalyzed reactions, right? Or acidic conditions. So remember in the first recitation when I mentioned kind of like the golden rules of mechanisms or whatever, where you have what was it? What was that first thing you said? Yeah. In acidic media, you'll have positive species. Basic media, you will have negative species. So that same thing is once again showing up here, right? And all those reactions we did before, right? After the nucleophile attacked, we had an O minus, right? Now we're under acidic conditions, right? So you're going to see we start with a protonated epoxide, right, which has a positive charge. So that conservation of charge, depending on the type of reaction conditions you're in, It's always going to be there, right? So nucleophilic conditions are generally basic conditions as well. I wouldn't try to use them interchangeably, but usually a lot of strong nucleophiles are usually are strong bases. So that's why all those things had negative charges, because it would be okay for it to have negative charges. Here, we're in acidic conditions, so everything is going to be either positive or neutral, right? So the first thing we start off with, right, is since you have an acid here, right? This is the most electron-rich thing here. Oxygen is going to want to protonate itself, and that is the first thing that happens, right? So first step, that. Let's go down this way. Now, as I drew earlier, right, we have the protonated epoxide, right? So your question was, acid catalyzed. Okay, so that's a good question, right? So the reason it happens, right, is once again, like I said, it has to do with the strength of the nucleophile, right? If you had, we could show this example right now, right? As this epoxide is right now, right, the only nucleophile present, right, will be a resultant of these when you break this HBr bond, right? Or even if you just had water, right? Let's just say we had water here instead, right? Like H2O, right? No reaction can occur, right? Because this water, it's only a moderate nucleophile. It doesn't have a full-on negative charge, right? It's not going to be powerful enough to, let's say, you know, come here and attack and kick open the epoxide, right? The kind of a attraction will never occur because the electrophile is too weak and the nucleophile is also too weak, right? When you have a full-on negative charge, it's going to be hunting for anything that's partially positive, right? Here, technically, you just have partially negative and partially positive, right? So that kind of a electronic attraction is not strong enough for it to have a reaction, right? So in acid catalyzed reactions, the way you make the reaction go forward, right, is you protonate that epoxide, right? And by protonating it, you're making it more electrophilic, because now, as we see here, right, the dipole is shifting towards hydrogen, positive. Oxygen wants to be negative, right? So this is pulling electron density, which is making this very partially positive, right? And that's why the protonation has to occur first, right? Because you need to make something a strong reactant, right? So in the case of nucleophiles, the nucleophiles are already nice and strong. They'll go and hunt carbons that are slightly partially positive, right? And they will do a reaction. In the case of the acid catalyzed reaction, right, you can't have strong nucleophiles present in acidic media, right? Because they would probably immediately get protonated, right? So the only thing you could have is floating around is like, moderate or weak nucleophiles, right? So you're doing all of this to make the electrophile much stronger, right? That's what I was saying. This reaction is electrophilic in nature, right? It's based off the strength of the electrophile. The first set of reactions we did is nucleophilic in nature. It's based off the strength of the nucleophile, right? Okay. Let's continue on with the question. Here. Okay, so first step was protonation. We have now increased the strength of our nucleophile, right? And now we could have what's floating around here is Br minus, right? So let's go this way, right? So now this is where it's important whether it's going to be attacking on the left or attacking on the right, right? So I guess let me ask you guys, which side do you guys think it will attack on? Left.
Hello? Excuse me?
Any other takers?
Sharu, can you hear me?
Left. Okay, looks like everyone agrees on left, and you are all correct, right? So in this case, right, you could call this, I guess, a primary position, right?
Hello?
And this is technically like a secondary position, right? So we don't really count the bond to the oxygen, right? So that's why this is primary, because this bond right here is just one bond, right? And then here, this has two bonds, right? Like that. So we can consider this secondary and we can consider this primary, I think your headphone, oh, 1 second. Oh, my bad. My thing was on mute. Okay. Were you saying something?
Yeah, hi. Can you hear me now?
Yep, I can hear you.
Okay, I was gonna ask, how come, you know how earlier, we were like, breaking up the epoxides? I'm still confused why we're not doing that. Like, why didn't we break down the left corner instead of?
Well, we're gonna do that in the next step, right? Because right now, no nucleophile has attacked to break open the epoxide, right? So the first step was just a protonation, right? So all we did was protonate the epoxide, right? In the second step, we're gonna break it open when the nucleophile attacks.
Okay, wait, I'm confused. Like, we couldn't straight up just like use the BR to like break it in the beginning.
No, right? Because initially, right, when you're in when you just have HBr floating around, it's going to be existing as HBr, or technically it might be HBr and Br minus, right? But Br minus is not going to really be a good nucleophile in this case, right? Because it's going to be solvated in a solution that has H plus all surrounding it, right? So once again, the nature of these reactions is electrophilic. So what happens is the H plus all floating around is going to come to that epoxide, protonate, and now this Br minus, right? Even though I know it looks like it has a full negative charge, but in this current solution, it's not going to be a strong nucleophile. But now you made a powerful electrophile, it's going to attract those charges, and then you could proceed with your reaction, right?
Okay. Can I just ask one more question? You might.
Yep.
I should probably know this by now, but like I'm still a little bit confused between the nucleophile and electrophile.
Mm-hmm. That's no problem. So nucleophiles, right, are things that are rich in electron density, right? So I don't know, examples are like, ETO minus, let's write it on the side so we don't open this question, right? So like, I don't know, hydroxide, CN minus, right? So things that are very usually, well, these are just examples of strong nucleophiles, right? And essentially they're things that are very electron dense, right? So a nucleophile is something that has electron density to give, right? It has a surplus of it, whether it's in an excess surplus with a negative charge or in a partial surplus, like, water could also be a nucleophile, right? The nucleophilic portion is the oxygen. It has 2 lone pairs. It doesn't have a full positive charge, but it does have electron density. Electrophiles, on the other hand, are places in molecules or molecules that have places that are lacking electron density. So very common ones are alkyl halides, right? So you have the Cl, right? And the Cl bonded to carbon, right? This is going to be partially negative. This is partially positive, right? So that carbon is lacking electron density, or it's electron poor, right? So when things are electron poor, they're going to be very good electrophiles, right? Another case would be like carbocations, carbonyls, right? All these carbons here have some sort of partial positive character because, well, in this case, it's a full positive character, right? Because things are pulling away electron density, right? So as Mohammed had said, the Greek translation, right? Nucleus loving, which makes a negative, and electron loving, right? I always like thinking of it in terms of electron density. Things that have electron density will act as nucleophiles. Things that lack it will act as electrophiles. So that's a quick Orgo 1 review. Let's go back to the question, right? So I will try to find one of my Orgo 1 recordings. I mean, they're in the folder available. Like, if you want to view, like, I think it's going to be chapter 6 or 7 stuff that goes over this. So if you want to watch that for a quick review of all that, because you're definitely going to need to know this, like, from the back of your head in your exams now. So we protonate it to make it more electrophilic, right? You could also say at the same time you're increasing the strength of the nucleophile, right? Because now there's going to be less H plus around it. But remember, the main thing you're doing is increasing the strength of the electrophile, right? I just brought up that solvating event because a lot of people are probably like, oh, but Br minus, right, has a negative charge, right? But like, it all depends on, the solution it's in, right? If it's covered by solvent, right, it's not going to do a good job as a nucleophile, right? Because there's going to be a solvent shell around it. So it's not going to act as a nucleophile. But if you make something electrophilic in that solution, right, then it's going to find itself to that, right? So as you're protonating this, yeah, you could say you're increasing the strength of this electrophile, and I guess you could say you're slightly increasing the strength of the nucleophile, but just think of these as electrophilic reactions, right? That's the main thing you're trying to do. Okay, let's just get back to answering the question here. So as people said, it's going to be left, right? And this has to do with steric effects, right? So in this case, it's more sterically accessible to attack the primary position compared to the secondary, right? So a good way to kind of think about it is, yeah, this, like, they both have partial positive character, right? But it's a lot easier for the nucleophile to access the place that has less R groups as opposed to the place that has more R groups, right? So this might not be the case when you get to tertiary centers, as we'll see that electronic effects will dominate. So in this case, the steric effect dominates, right? And this kicks open, and boom, you get your final product, which is alcohol halide. So let's try to draw this properly. OH and BR, right? Should be our final product.
Sharuk,
Mm-hmm.
didn't you say that the BR was not going to be the nucleophile?
No, it is going to be the nucleophile. I never said that.
I thought you said it has a lot of H's around it, so.
Yeah, no, it does. That's what I was trying to answer. I think it was your question or Charmine's question, that why it doesn't just immediately attack, right? Why it has to protonate first, right? Because in the beginning of the reaction, it's not going to be, it's going to be too solvated, right? But when you create a powerful electrophile, this interaction can happen, right? That's the basis for this whole interaction, is the electrophile is very, very strong, right? So the BR will find itself to that path, right? It is the nucleophile in this reaction, right? It's just initially, right, why this reaction doesn't just start off as BR minus attacking, right, is because this electrophile is not strong enough at that point, right?
Okay.
But it is the nucleophile. Yeah. Okay. Let's do another one. And then I'll give you guys some rules, basically, that can basically kind of surefire things that you'll always get because the acid catalyzed ones, as I could see and I've seen in the past, like, these are the more complicated ones, right? So Ali, or Ali, I don't know how you pronounce that. Well, what if that is, well, it attacks that side? Yep. So I'm going to do a couple of examples with the competition. Let's see.
Sharuk, one more question. So what role does the H2O play there?
The what?
The H2O?
Oh, sorry. That was just me giving another example. Sorry about that. That's not in this reaction. Yep. Okay. Where are we? Let's see which question I want to do. Okay, I guess we could do D. Right. So here we have E. And H2SO4, which is just our acid catalyst, right? And our solvent and nucleophiles. So this is a hydrolysis reaction, is water, right? So this is acid catalyzed hydration. You guys probably seen this in Orgo 1. Very commonly done reaction to essentially add water across a molecule, right? So once again, when you're in acidic conditions, right, technically you have H3O plus floating around, but also you're going to be protonating things that are electron rich, right? So that's why it's, again, proton is going to, so I'm just going to write it as H plus. If you want, you could draw out the whole structure. If you want, you could write H3O plus or whatever, right? I think for the most part, both boson and Professor Biscoe accept if you just grab a proton, because It's not very important where the proton comes from. You know it's in solution. So only strong nucleophiles can break the epoxide. Yes. So in the first step, when you have a strong nucleophile, right, it's going to break open the epoxide. That's the first step. Then the second step is protonation, right? In acidic mixtures, the nucleophile and acid and everything, it's all in the same solution, right? So because of that, right, because it's in protic conditions, right, and there's an abundance of protons already, right, the first step is going to be the protonation of your epoxide, followed by breaking open the epoxide. Okay, boom, right, grabs a proton, protonated. Now we have a powerful electrophile, and now our nucleophile is going to be what in this case?
Water.
Water, yep. T and Me, right? Let's see, H plus, okay. So now next step, right, is our water. It's going to, let's go down this way. I'm going to write water as OH2, so it's easier to use as a nucleophile, right? So now, what do you guys think is going to be left or right side? Okay, so we have mixed confusion. That's good, right? So let's clear that up, right? So in the first example, right, we had a primary position versus a secondary position, and steric effects just greatly like outmatch any sort of electronic effects there, right? It's just easier to attack a primary position. It's more accessible, right? So steric effects dominate, right? Now, when you have something like a secondary, right, we can call this secondary. We could call this tertiary, right? This has 2 R groups. This has 3 R groups, right? Now, electronic effects, exactly as Dominic said, are going to dominate over the, what's it called? Steric effects, right? Because now, at this point, right, when you're secondary and tertiary, you both have enough R groups that whenever your nucleophile is going to come, there's going to be some electron density in its way, right? So, yeah, technically this is sterically worse because there's 2 R groups there, right? But at this point, right, the electronic effects dominate, right? And this has to do with hyperconjugation, right? So remember what I said was these are both partially positive centers now. Oh, sorry, let's draw it in the second thing. So these are both partially positive, right? But what stabilizes the partial positive center better, right, and essentially makes it a better electrophilic position, right, will be the tertiary position, right? Because you have 1, 2, and 3 R groups donating electron density into that carbon, right, which will make that, partially positive carbon more stable, right? Because remember the stability of carbocations, right? It goes down as we increase or decrease R groups, right? So the same kind of, effect is happening here, right? Is because you have more R groups, you're stabilizing that partially positive charge better. If you're stabilizing that charge better, that means that carbon is going to be in time, it's going to be more, you're going to find it to have more partial positive character than the other carbon. And because of that, the electronic effects dominate, right? Because at that point, it's going to be the better electrophilic position, right? So the OH2 or H2O is going to go and attack on the left side. And now I can kind of write my little rules on the side. Whoops, let's different color arrow, right? So it comes in there, right? It's going to break this open, right?
I'm sorry, can you re-explain why it attacks the left side instead of the right?
Yeah, so they're both, right, I guess secondary versus tertiary, right? They're both, have some sort of steric hindrance or whatever, but like basically, actually just forget the steric part, right? It all has to do with electronics, right? When you have 3 R groups on it, right, it will stabilize that partially positive center a lot better, right? Which in turn makes it a better electrophile, right? And that was something called hyperconjugation, right? When you have more R groups around a carbocation, right, as I mentioned here, right? This is less stable, right? So remember, tertiary carbocations are more stable than secondary, more stable than primary, right? So that kind of same effect is being played here, right? Except it's not a full-on positive center, right? But because it has partial positive character, the R groups, right, they're going to stabilize this a little better, right? Which means that if you were to like, look at these molecules at a molecular level, you'll see that the electron density, it's gonna spend less amount of time at this center because it's more stabilized, right? And because it's more electrophilic now, right? Because it's a better electrophile, right? Because of that hyperconjugation, that electronic effect dominates, right? And that's kind of the whole thing in terms of sterics versus electronics, right? Is that when you have three R groups on it, the partial positive character is better stabilized, and that makes it a better electrophile, right?
Well, this just like confuses it because like all this time we were like
Talking about sterics, right?
yeah, now all of a
Yeah.
sudden
So
it's like
this is stuff that people have done extensive research on, right? And you could probably find papers published on it from like maybe 100 years ago, or who knows, 70, 80 years ago, right? And that's what they found, was that when they did these epoxide reactions, right, they probably, I mean, at first they probably couldn't explain it because they would accept the same thing, the least sterically hindered position, right? It's going to, you would expect that's where the nucleophile to attack, right? But when they got the product on a tertiary position, they're like, okay, what's the explanation for this? And then they figured out that it has to do with the electronic effects, that at that point, 3R groups are going to make that carbon a better electrophile, right? So let me read the chat since we had a bunch of stuff. So when we are presented with primary or secondary, we pick a primary, right? So this is once again all under acid catalyzed condition, correct? Right? When we pick tertiary versus secondary, we always pick tertiary. Yes. And let me write the little rules that I have here. So this will be very clear, and you could always kind of refer back to them, right? So once again, this is acid catalyzed.
wait, so like sorry, but like how are we supposed to know if we're looking for the more stable one or if we're trying to do the less sterically hindered one? Like how are we supposed to assume like which is the right way?
You just have to look at both positions, right? Whether you have a primary, secondary, or tertiary, right? And then you'll know which effect dominates, right? So like as someone said before, primary versus secondary, steric effect always dominates, right? Secondary versus tertiary, electronic effect always dominates. And then primary versus tertiary, electronic effect also dominates, right? So that's what I'm
write
gonna
all that down.
Yeah, I'm just about to write it down right here. 1 second. Okay, so what do we have here? So acid catalyzed epoxide reactions. So let's draw all these, right? So these are, the book doesn't have the second case I mentioned. So for some reason, I don't know why, the book only gives you example of 2 cases, but even though in the chapter it mentions the 3rd case. So here we did examples. So this is what, this would be 1R group. So this would be secondary and primary, right? So here, steric dominates, right? Now, if you have something like primary, right? Right? Electronic dominates.
Wait, the
Right?
second one was primary and what?
So this is, oh, sorry, primary and tertiary, right? So primary versus secondary, steric always wins, but primary versus tertiary, right, which is the case that unfortunately we don't have a problem to do an example with, right? Electronic dominates. So basically, whenever you have a tertiary center, the electronic effect will always dominate, right? Because it's just a better electrophile. It's just more stabilized, right? And if you want to think about it, right, it has to do with like the bond length, right? I don't know if the book mentions this, or maybe Professor Biscoe might have mentioned it. I didn't want to, because I was trying to make sure we have enough time to do the chapter 16 stuff. But the same thing, if you guys remember from oxymercuration, demercuration, right? When you have that kind of tri-membered ring, right? One bond is shorter than the other, right? So the same thing is happening in the epoxide, right? Is that essentially when you have a tertiary position, right? The oxygen, right? It's going to just be closer to the primary position, right? Because essentially, right, let's say this is positive, whoops, right? So if we had like 2 bonds here, right, and this is tertiary, right, you're gonna see that this oxygen, right, is gonna move closer to this one, right? Because this bond between the oxygen and tertiary, it's more likely to break, because if it does break, that partial positive charge is stabilized a lot better, right? So if you broke the other bond, right, the partial positive charge won't be stabilized as better because it's going to be a primary position, right? So if you think about it in terms of bond length, it might be easier to see why the electronic effect dominates, right? And you guys probably seen this when we did, or in Orgo 1, the same thing happens in oxymercuration, demercuration, when you're doing a Markovnikov addition, right? It's going to be the mercury is closer to the side that is less sterically hindered, right? Because this holds partial positive character better, right? So I didn't want to get too much into that because I want to try to do examples or whatever. I think the book might mention this bond length stuff, maybe Biscoe did as well. But that's a good way to always think about it. Why, right? When you're breaking the oxygen-carbon bond, which bond is more likely to break? And the bond that's more likely to break is the one between oxygen and a tertiary carbon, because then the positive character on the tertiary carbon is more stabilized. And with Grignards and all strong nucleophile, it's always the less sterically hindered position, right? That's why I wrote acid. I'm just going to leave that there. And then let me draw the last rule, which is here, right? So you could refer back to this little chart or section, right? So this is R, this is R1, R2, right? So this is secondary versus tertiary. And once again, electronic dominates, right? So these are all 3 cases you'll see in the acid catalyzed reaction, whether one carbon is primary versus secondary, right? Primary versus tertiary or secondary versus tertiary, right? So steric only dominates when it's primary versus secondary. Anytime you have any tertiary carbon, the electronic effect will always dominate, right?
Sharuk,
Yeah.
if that's the case with the third one, then I'm confused by example F, because in example F, when we had the LiAlH4 thingy,
That was not an acid catalyzed reaction. That was a strong nucleophile reaction, strong basic reaction, however you want to look at it, right? This is only for acid catalyzed reaction. That's why I wrote it on the top, right?
Wait, what is the difference between acid catalyzed reaction and strong? Like, it's just so much vocabulary.
Acid catalyzed reactions mean there's an acid present in the reaction medium, right? So in this case, we had HBr, or we had sulfuric acid, or we had, I don't know, whatever sort of acids. And the other one, all we had was the nucleophile and whatever solvent you're using, right?
Wait, so these 3 rules you wrote, like, on the right, this is only for acid catalyzed reactions.
Exactly.
Okay. And like for other reactions, like the strong nucleophile ones, it's always going to be what, like sterics?
Yeah, so it's always going to go for the least sterically hindered position.
Is the nucleophile, the strong nucleophile one, same as Grignard reactions?
Yeah, so Grignard is an example of a strong nucleophile, right? You have nitriles, hydroxides, ethoxides, hydrides, a couple of them, right? But the end of your chapter has like a little list that separates the types of reactions. But essentially, if you see an epoxide reaction and you see an acid present, follow these rules, right? If you see an epoxide reaction that's a strong nucleophile, right, just go for the least sterically hindered position. So primary, secondary, steric hindrance affects the most, secondary versus tertiary electronic, and primary versus tertiary electronics. Yep, exactly what you said there and what I wrote on the side here. If there's any more questions on this, let's save this to the end of, like after this we cover whatever we can today. I'll take any more questions. I'll stick around. But I want to make sure I need to get to chapter 16 because we're spending a little bit too much time on that epoxide stuff here. So we'll just do one more example of this. Oh, wait, we didn't finish this example here. So anyways, water is going to come in, it's going to attack, it's going to break it open, right? So now you have OH here, right? ME here, right? Yeah, stereochemistry is gonna apply here. Let's make sure I do this correctly. If I draw the OH like this, or OH2 this, then that would mean the other two are flipped. If you draw it on the bottom, it shouldn't matter. Yeah, this is why it's depending on like which side is planar, it's a little bit annoying to draw it. So this should be OH2 plus, and then this should be a wedge, second dash, wedge. This should be ME, should be ET. If you technically came in from the bottom, I guess you could preserve the stereochemistry, because then the oxygen will be opposite of oxygen. Then you wouldn't flip the signs because then it would still be flipped based on how you did it. I have to double check that though, if the signs are the right way. But anyways, next step is just another molecule of water is just going to come and deprotonate it, right? The hydronium over there. Yeah, I mean, it shouldn't be too big of an issue, right? Like I said, it depends on which groups are linear. So here the oxygen and carbon are linear, right? So if I drew it this way, technically you flip the sign. But if you have the oxygen on the bottom, right? Remember what's it called? The rules for defining like R and S, right? If I had oxygen on the bottom, the way the clockwise motion would work, then you would leave the signs like on the same thing. So that's why I just draw it on the top. It might look a little weird, but that way I could flip the signs. But technically, if you drew it from the bottom, I think you could leave the methyl on the dash and ethyl on the wedge. Like I said, I gotta put this in ChemDraw and check. But it's not too big of an issue now. If you understand there's inversion there, it's kind of all that matters. So final product, OH. ET, ME, OH. Yep. Okay. Do you guys want to do one more epoxide question or continue on to chapter 16?
I want to go to chapter 16 because I'm afraid we're not going to have time before our exam.
Yeah, okay, good. Hopefully everyone's clear. Like any other questions with the epoxide stuff, we will get to later. But let's start chapter 16 stuff. Okay. No, it's already been over an hour. We'll do what is it? Thermodynamic versus kinetic control, and then we'll take a small break. I need to get some water and stuff. Okay, so this is all conjugated pi systems and pericyclic reactions. Okay, so these are, well, at least when we get to the pericyclic stuff, those are fundamentally different than any other reaction that you have, because every other reaction is usually what we call ionic in nature, right? That you have some sort of positive or some sort of negative thing coming together, right? Pericyclic reactions, on the other hand, right? They don't go through any sort of ionic mechanisms, right? They go through certain transition states, right? That's why they're classified different than all other types of reactions, right? Is because they're very unique. And it kind of all has to do with the orbitals, right? So let's start with electrophilic addition first. Hopefully that was enough for you. I have to scroll down though right now to start doing this. So you could access these notes later. Okay, so electrophilic addition on conjugated dienes, right? So let's find a good example of this. Right, so this is where things like thermodynamic and kinetic control come into play, right? So let's do 16.9. Use right. So start with A. Now, it says predict the products for each of the following reactions. In each case, determine which product will predominate, right? I'm gonna kind of change this question where it's gonna be something more similar to your exam where essentially what I want to know, let me draw out the structure here, right, is under two different conditions, which product dominates, right? So we have HBr in this case, right? So I guess we can write sub I at, did you guys, did he tell you room temperature or 40 degrees? Or, I mean, it doesn't matter. Basically, if it's above room temperature. So room temperature to like 40 degrees, however you see it on your exam, it's the same thing, right? And then the other one is 0 sub-zero usually, 0 degrees Celsius. Did he give you guys 40 degrees Celsius or did he say room temperature? It doesn't matter. It just has to be above room temperature, really. Yeah, room temperature. That's why I don't know why the book says 40 degrees, because I mean, I guess you get slightly better yield because you have more energy in the system, but you could run these electrophilic additions at room temperature easily, right? The main important thing is for kinetic control is when you do 0 to sub-zero, right? You need a very low temperature, right? So that's why I wrote room temperature to 40 degrees C, because it doesn't really matter. Okay, so we're gonna do the reaction mechanism and we're going to, what's it called? Predict the products for this, right? So electrophilic addition, right? You guys already did this in chapter, what is it, 8 in Orgo 1, right? So it's pretty straightforward, right? In that the first thing that you start off with, right, is going to be a protonation, right? Because you have alkenes here. This and this, these are electron rich. You have a proton there from the HBr. So one of these is going to protonate itself. Luckily for us, this is symmetrical. So it doesn't matter whether you choose top or bottom. For convenience sake, I will choose the top. So let's make this bond a little thing, right? So the first thing that happens, we protonate that. So remember, we draw the arrow from the alkene, right? So I mean, you could probably draw it from a corner if you want. I just draw it from the middle of the alkene because it doesn't really matter. And next arrow here, right? And we get our first intermediate, which looks like this. Right? So in case it's not clear what happened here, right, is the double bond, right, grabbed a proton, right? Technically, if you want to think about it, right, this is where the other proton ended up, right? So what is that? I guess a Markovnikov addition, right? Or if you want to, you could think about it two ways, right? You could think about, like, I know the rule they tell you in this textbook is that the hydrogen ends up at the position with more hydrogens, right? Or whatever, right? Always think of when you're doing that first protonation, create the more stable carbocation, right? So essentially we had two positions, right? You could be at this carbon, right, with the arrow, or the other tertiary carbon, right? Which carbocation is more stable, the tertiary or secondary? Tertiary, right? And therefore, that's the carbocation we end up with, right? So at this point, now there's two pathways this can go through, right? It can go through the kinetic control pathway, right? Or it can go through the thermodynamic control pathway, right? And that depends on the temperature of the reaction, right? So if we were to do this as 0 to sub-zero, right? Like -78 or something, so probably an ice bath is good enough to do this, right? Or a salt ice bath if you want it just slightly below 0, right? So we had this under 0 degrees Celsius, right? What's going to happen now is instead of any sort of rearrangement, right, we're going to have Br minus, right? Is this going to, the resultant kind of nucleophile that formed now, it's just going to go and it's going to attack and substitute at that position, right? Or add at that position, however you want to think about it. And then this has something, I guess you can call it like a, I mean, it's called the proximity effect. Essentially is as this HBr forms, right? Like if I were to draw this HBr closer, right? Like HBr was close while it grabbed this electron, the Br minus is in proximity of a carbocation that's forming, right? So while this is all happening, the Br is very close, right? And essentially when you're at a low temperature, you don't have enough energy for rearrangement. So what happens is the Br minus just, oh, choose a different color arrow, right? It's going to just attack at that position, right? And that's something called the proximity effect, is essentially when this reaction is occurring, right? Maybe let me draw it down here a little better, right? Is HBr is very close, right? So as this grabs here, right? This breaks off, right? The Br minus is going to be floating around very close to that newly formed positive charge and immediately just go and attack there, right? And that's called the proximity effect. And it's very, it occurs a lot when you have a very low temperature, right? Because, I mean, actually it occurs at every temperature. It's just your final product will dominate because you have a low temperature. You don't have enough energy for the reversible reaction, right? So this goes forward at 0 degrees Celsius, right? And then you get your first product. And is this the 1,2 or the 1,4 adduct? The type of addition it was, right? So if we were named this 1, 2, 3, 4, right? This is called a 1,2 adduct, right? 1,2 adduct, right? Because it is essentially adding a proton at position 1, and then the nucleophile in this case was added at the 2 position, right? So you have a 1,2 addition here, right? So now if you're at 40 degrees Celsius, right? So this is what's called kinetic control, right? Because it all has to do with kind of how fast this reaction, the rate of this reaction, the rate of this HBr, right? Instantly adding to the second position there is a very fast occurring reaction. And the way we control it is through low temperatures, right? Because we know it basically happens very quickly, right? And the energy barrier for this reaction is much lower. If we were to draw it in a, maybe when you do exam review, I'll do the energy diagrams, right? But essentially for that second step, you have a very low energy barrier, right? Because the Br is so close, right? So this is kinetic control, right? So now what if we did the same thing here, right? But we had it at like room temperature or 40 degrees Celsius, right? Well, now, right, what will happen is actually the Br minus, technically it still attacks, right? So I just want to show this because it's, let me draw this down here so we're not confused. So this is the second pathway, which is going to be at room temperature now. So now the Br minus, right, that proximity effect is still happening, right? But now actually I will draw this as a reversible arrow, right? Yeah, I'll try to do that. That's usually what I do for review sessions. I don't really have, well, actually, no, there might be some of old bosons exams for those here from bosons class. Checking my OneDrive, I have like 1 or 2 of his exams and Bisco's exams are much different in their style. But for the exam reviews, even when I did bosons class, I would always review the Andia Bisco style exams because they do their exams similar. And it's usually good enough to get you to do well on bosons exam as well. Just boson has a lot of, I think, multiple choice kind of style questions. So it's like I said,
Nope.
slightly different. He's not having multiple choice. Oh, okay. Yeah, it's usually like 20 plus questions. Like, I forget. It's a if there's one exam in the folder, you'll see it's a little bit different. There's no multiple choice anymore. Oh yeah, so he had like, I shouldn't say it's multiple choice. It's like 1 or 2 questions that are multiple choice in there, but for most part, it's very small, short answer questions. It's like 25 of them. Way back when, at Bologna. She passed away though. Anyways, oops. Okay, so this step, technically, I just want to show this because this is what's actually happening, right? Is the BR is still going to attack at this position, right? Because of the proximity effect, right? So you do get this happening, right? But now because you're at room temperature, right? Once again, this is all occurring at room temperature or 40 degrees Celsius, right? Once again, this is an irreversible reaction, right? I mean, not irreversible, reversible reaction, right? So it's essentially like this will happen, but you have enough energy to go the backwards pathway, right? So this
You missed
product
the
still,
methyl on the bottom.
what happened?
The methyl on the bottom next to the alkene.
Oh, thank you. Yes, the methyl on the bottom, right? So the reverse is still happening. So this proximity effect, it's still going to occur at elevated temperature, right? It's just that you have enough energy to resurface it. So this is still the kinetic product, right? And this is still going to form, right, in the thermodynamic control as well. And technically the other product forms in kinetic control as well too, right? It's just that you have enough energy for this to be reversible now. So now what happens, right, is the pathway, which I'm going to draw in orange, right, is the more dominant pathway, right? Is now what happens here, right, is because you have enough energy, right, instead of having this kind of first step occur, your alkene is going to rearrange, right? So your alkene is going to rearrange. And then let's just draw it all in orange for simplicity's sake, right? So now you have the alkene here, right? You have a methyl group here. We have a partially positive carbon there. Let's draw it actually inside so it's easier to do the attack, right? And the reason why this orange pathway is going to dominate at thermodynamic under thermodynamic control. Resonance kind of has to do with it, right? It does technically have an additional resonance structure, but look at the stability of the alkenes. Let's call this A and let's call this B. Which has the more stable alkene? Why? More substituents, right? So that's the main reason, right? So going from A to B, right? Your alkene, right, is going to become more stable there in the intermediate stage, right? Remember, when you have more substituents on your alkene, it's going to be a more stable alkene, right? So you're going from a tri-substituted to a tetra-substituted alkene, right? Therefore,
I thought the question, somehow I just heard you say which one is more stable and thought about the carbocation.
Yeah, so it doesn't have to do with the carbocation in this case. In this case, it's the stability of the alkene, right? Because technically the carbocation is resonating between the two structures, right? So as I think Mohammed there said, or somebody, about the resonance, that does in part of it, right? That does have additional resonance structure, right? But also it has to do with mostly that the alkene in structure B is a much more stable alkene because it has a higher substitution, right? And because of that, right, the final product will be lower in energy, right? So now we can go ahead with this pathway, Br minus, and boom. This is the 1,4 adduct, right? So in both kinetic and thermodynamic control, you're gonna get both products, right? And let me just draw out this product.
But on high temperatures, which one is going to be more major? I think the kinetic one.
High temperature is major. This is the major, right? So
So this is thermodynamic.
yeah, so let me just
Okay.
write that under here. This is thermodynamic. So kinetic control, right, has to do with the rate of the reaction, essentially, right? And because of that proximity effect, that's why you get that as the major product, the 1,2 adduct, right? Here you get what's called the 1,4 adduct, right? And the reason is with thermodynamic control, you could kind of think about equilibrium, right? It has to do with the relative, like, I guess potential energy or energy levels of the product, right? If you look at the top 1,2 adduct, you have a tri-substituted alkene, right? The bottom product has a tetra-substituted alkene. So which product do you expect to be lower in an energy level? The 1,4 or the 1,2?
1,4.
It's the 1,4, correct, right? Because it has a more substituted alkene, right? It's just the pathways
So-
differ. Now your textbook, I think, has a little nice diagram, but essentially what's happening, right, is that the second step has a lower barrier of energy, right? Which is right here, the one I just underlined, right? Because of the proximity effect. So you could, that's why it's the kinetic control reaction, because this occurs really, really fast, right? So if you're given, like, sometimes there's like a individual problem, right? Like it'll give you like an electrophilic addition, and they'll ask you, like, show the two pathways of this reaction, draw an energy diagram. So right now I'm not going to show the energy diagrams. Later on I will show them when they're doing exam review. So if this is a separate question, you need to know all of this, right? The mechanisms and the pathways, because he'll probably ask you for mechanism and pathways and explain which is major and which is minor, right? If you're given this on, like, remember that question I showed you that has like 8 parts on it? If you're given it like where you're basically just given the, HBr and a temperature, then you just have to draw the major product, right? So it depends on the kind of question you're asked on an exam. If it's a small question, then just draw the major product, right? If it's a, like a full-on question, you need to show this mechanism and, like, how it all happened. That's why I just wanted to cover it all in one question, right? Yeah.
I have a question. So the thermodynamic one is always the one that's more stable, and the kinetic one is the one that's always less stable.
Well, yeah, in terms of energy level, yeah, the thermodynamic product is lower in energy always because it has a more substituted alkene, right?
Okay.
And then the kinetic one is slightly higher in energy, right? But if you kind of look at the pathways they take, right, this, I guess the activation energy of the second step, so we'll call this EA1, and then we'll call this EA2, right? EA1 has a smaller barrier than EA2, right? So thermodynamic minor product is 1,2, is reversible, but major 1,4 is not, right? I mean, technically they're all reversible. It's just that it just dominates, right? It's just like, because it's an equilibrium process, right? What's essentially happening is, remember I said nature prefers the lowest state of potential energy, right? So when the kind of equilibrium occurs, you're going to see that the 1,4 adduct dominates more than the 1,2. You're going to still see both, right? It's just, in terms of yield, you'll see like I don't know, 70 to 80%, maybe even higher for like the 1,4 under higher temperatures, and then you'll see the same thing occur for low temperatures, right? And then you just separate your products.
So at the lower temperature, which product is forming? Is it thermodynamic?
Both will form the major product. So let me just make this clear here. So kinetic control, right? So actually here.
Can you relate this to temperature too? Because I get that the thermodynamic is more stable, the kinetic is less stable, but which happens when is my question, or which is major when?
Okay, so that's kinetic control, right? It's at a lower temperature. Both the 1,2 and the 1,4 still form. The 1,2 product is the major product. So that's why I wanted to show this entire mechanism, because this is going to occur at both things. It's just that orange pathway is going to happen a lot more in higher temperatures. The top, the top pathway there for the kinetic control is going to happen a lot more for things. So now let me write thermodynamic control, which is the same thing. So this is at higher temperatures. Just write room temperature to 40 degrees, depending on what you might see on your exam, right? Both, once again, both the 1,2 and 1,4 form, right? But now the 1,4 is the major product because we have enough energy in the system to go that pathway, right? So once again, that orange pathway takes more energy, right? Because the alkene has to, switch positions, right? So that barrier of energy is higher, right? But the final product will be lower in energy, right? The book, let me see if I could find a little section on this that has a diagram. 16.5, right? If you want a clear diagram of what I'm talking about, and we'll do this again once, probably during the exam review. Yes, so 1,4 still occurs under kinetic. Both will occur, right? I just showed both these pathways, they occur at both temperatures, right? It's just one dominates over the other, right? So 16.5 in your textbook is a little portion that explains this a little with like diagrams and stuff, right? But as I said here, under kinetic control, you're at lower temperature, both products form, but the 1,2 is the major, right? Thermodynamic control, higher temperatures, both of them form, 1,4 is the major, right? Okay, so because I really want to get to Diels-Alder's reaction, I'm only going to do one example of this. What problem was this? 16.9. If you want to test out the major, this question doesn't ask for the mechanism. If you want to draw it out, feel free to. Right, I would highly suggest doing the other letters under this problem, 16.9 for practice, because the question just asks you draw the major product or draw both products and then tell you which one is major, right? Where is it? Here, we'll do one more, but we're not going to do the mechanism here. We're just going to draw products out. So we could, like, if this was a more simpler question on your exam, as someone mentioned, right, how you would see it. So if you were given, like, in question 3 or 4 on your exam, for those who are taking the SCO, right, if you were given this question, or like if this was a question on Boson's exam, right, where all he gave you was this and he told you to draw the major product, first you look at the type of reaction it is. Okay, we have a conjugated diene, we have an acid, right? We have a halo acid, so this is most likely an electrophilic addition, and it's at a low temperature, right? So then all you have to do is, if you want, could just label these, right? And which product are we going to expect, 1,2 or 1,4 as the major, right? If we only want the major here. 1,2, right? So if we were asked for the major product here, the answer would just simply be Cl, that, boom, right? And if we change it to HCl and like 40 degrees Celsius, then the major product in that case, right, is going to be Cl, right? And if you were asked to draw all products and predict which one is major and minor, you would draw both of these and then select the major one, right? So once again, I'm just going to write this is major under all of these. Okay, so that's enough for electrophilic addition. Let's do Diels-Alder. I'm just going to skip. You guys need 5 minutes? No? Okay, we'll take 5 minutes. That's fine. We're going to end up going over to probably like, I don't know, but it's fine because I'm going to make sure we do all the Diels-Alders today. We might not get to the cyclo additions, but that's fine. But Diels-Alder, I want to make sure I cover all of, because that is 100% going to be on your exam on both classes. So we'll resume in like 132, 133.
Sharuk? Sharuk?
I think he took his headset off, or he just went mute. So I don't think he hears you.
All right. Hopefully everyone is back. Okay, so Diels-Alder reactions, right? So these are the first kind of pericyclic reactions you guys learned. This is specifically Well, pericyclic reactions are just reactions that go through like what's it called? Transition state where you don't have like ionic species, right? Like, you know, how in all these reactions we had something like negative or positive coming together, right? This is usually, you know, rings forming, right? And like there's a couple of different types. The two most important ones are cycloadditions and sigmatropic rearrangements, right? Those, in my opinion, are the most important ones. I think the other one was the electrocyclic. I mean, yeah, they're kind of important. I mean, I'm not going to say they're not. I'm sure some chemist somewhere out there probably finds them important, but the main ones that are studied a lot are cycloadditions and sigmatropic rearrangements, and specifically the Diels-Alder, right? Is a 4+2 cycloaddition, right? Essentially, it involves an electron system where you have a 4-electron system combining with a 2-electron system. So you see the case in all of these here, right? You have 4 plus 2, right? So it's a 4+2 cycloaddition, right? Because you form a cyclic ring when they come together, right? So let's start with A, which is a very simple one. And I think I accidentally messed up this here. Okay, should be like that, right? So in A over here, right? Basic mechanism of a thing is basically one of the double bonds. So this species is called a diene, right? And this is the nucleophile. Oops. So I couldn't write that correctly, right? So the diene is what is electron rich, right? Essentially, it has a lot of electrons, right? That's what electron rich means. And it usually has a very good HOMO, right? If you were to look at this in terms of molecular orbital theory, right? It has a very good HOMO, right? The dienophile, right? As the word suggests, it's something looking for a diene, right? But it's usually lacking electron density. And generally, you'll see electron withdrawing groups, as you see in all these example here, right? Here you have this ester group, right? So this electron density is technically, if you drew a resonance structure, it's pushing the carbonyl is withdrawing electron density for it. Same thing over here. You have electron withdrawing groups, right? One second, I'll answer that. And then same thing here, cyanide is electron withdrawing, right? So HOMO and LUMO, right? Highest occupied molecular orbital, right? LUMO is lowest unoccupied molecular orbital, right? So the best, this is also true for, I'm not going to talk about the nucleophiles, electrophiles. So right now for dienes have very good HOMOs, right? And dienophiles have very good LUMOs, right? And that makes sense because the HOMO, the one that the diene has, right, is the more electron-rich molecule, right? So it needs to have a good HOMO, a good occupied molecular orbital, right? And the dienophile, which is what's receiving the electrons essentially, right? It needs to have a good LUMO, which is the unoccupied molecular orbital, right? So these HOMO-LUMO interactions is how I guess chemists have kind of rationalized how these pericyclic reactions work, right? Probably next week, I'll start off with like something called thermally allowed reactions, right? I think you guys should have learned that. That's kind of whether things are allowed based off orbital symmetry, right? Did you guys learn about that? Orbital symmetry, like conrotary, dexrotary, whether something is thermally allowed or photochemically allowed?
No, sir.
No? Well, I will ask Professor. Well, did you guys finish chapter 16? Like, did he start chapter 17? So he didn't finish chapter 16? You just finished Diels-Alder. Okay, cool. All right, so if you haven't gotten, okay, so then you probably, because I know usually he'll do the thermally and photochemically allowed stuff because it's important in understanding molecular orbital theory. But anyways, right, so that's a brief little tidbit on the Diels-Alders, right? The basic mechanism works, right? That your diene, one of the double bonds, attacks here. So you're forming a new sigma bond here, right? Then in return, this alkene, right, is going to attack the end of another double bond there, and this double bond pushes to form a alkene in the middle here, right? If I drew this out in terms of molecular orbitals, you will see that the HOMO, right, of this diene will be the orbitals will be aligned in the same phase as the LUMO of the dienophile, right? We'll probably do an example of that next week, right? Where if he probably showed it in class, right? Did he show the molecular orbitals or no? Like the phases, right? And how they interact. He did that, right?
Yeah, he did. Could you go over them again? Because I never like understand those drawings. Please?
So I'll do that. I'll do it next week when we do the rest of this chapter, because right now I want to go over the outcomes of this reaction, like products and regiochemistry, stereochemistry, all that, right? So we'll do the molecular orbital stuff probably next week. Right now, let's just do as much practice as we can as, answering the questions, right? So this is the basic mechanism, right? And if you were to overlay the orbitals, you would see that the phases at the end orbitals for the diene match up with the phases of the dienophile, right? So anyways, right, you form 2 sigma bonds and you form a new pi bond. That's the general outcome of the Diels-Alder reaction, right? And, this was and still probably is a very useful chemical reaction, because you could essentially, it's a cyclic reaction. You form a new cycle, and then you could do all sorts of other reactions on top of it, right? So now we form, right? So actually, to make this a little simpler and visually easy to see, right? So this was the original dienophile, right? We'll say this is the new double bond that formed, right? This is the new sigma bond, right? And then this was where the dienophile was, right? So those 3 pink bonds are those new bonds we formed, right? We formed 2 sigma bonds and 1 new pi bond, right? And we removed 2 pi bonds that were originally there. Now the rest of the groups attached, right, are dependent on whether the dienophile is cis or trans. So in this case, what kind of alkene is this, cis or trans? Cis, right? So the 2 largest groups are on the same side. It's also symmetrical. So we would consider that cis, right? If the groups weren't the same, but they're on the same side, then that is Z, right, for zusammen. And then E, I forgot the German word for that. That is for the same as trans. But anyways, so are these going to be on the same side or the opposite side?
Those are going to be probably both looking, one looking down and one looking up.
So for this one looking down, one looking up. No,
Which
right?
one
Because
are you talking about?
A, the one we're doing here, right? So as
No,
people
I mean
have,
the OME or the double bond O.
no, I'm just talking about the product. Anyways, so when you have the product here, right, when it's a cis alkene, right, or I guess Z alkene, right, the groups end up on the same side, right? So on the final product, we accept they have to be facing the same direction. So you could draw wedges or dashes. It doesn't really matter in this case because it's not a bicyclic, right? I'm just gonna draw it like this. And in this case, the stereochemistry, 1 second, let me draw out the product. Let me just make sure. I don't think it will have any stereochemistry because there is a axis of symmetry here. Flip. Yeah, so this should be also meso, right? And how I did that quickly, right? For those, like whenever I see something symmetrical, I always draw a line of symmetry between it, right? And then I quickly in my head try to see if I could rotate it around that line, right? If I get the same thing on the rotation, right? And this is something, you gotta kind of do fast, right? You have a meso product, right? So if this group was slightly different, if this was an O-ethyl, right? Then this would be technically racemic. But in this case, right, because there's an internal line of symmetry or axis of symmetry, right? This would be like one group would be R and the other would be S, right? That's called like internal enantiomers, right? So this would be meso. You could also draw this I think somebody said both wedges. Yeah, Mohammed, that would be right too. Technically, you would just be looking at it from the other side, right? If I was to flip this over, right, it would just be the groups are coming towards you, right? But it's the same exact product, whether you draw it on wedge or dash in this case, right? When you start dealing with different stereochemistry, then the wedge and dash are kind of important. But in this case, since we have a meso product, it doesn't matter whether it's on a wedge or dash, but they both have to be on dashes or they both have to be on wedges, right? Okay. Why would the two carbon groups attach to the specified carbons, right? So what do you mean by that? Like, let me try to circle. Like, so at this carbon and this carbon?
I think she means something that I'm also having trouble with. Like I'm confused. Like the second structure where like it's like basically the first structure took over the second structure's part. Like confused. Like how did they combine together? Like where are the
Oh,
lines
okay.
going?
1 second. Okay, let's try to maybe draw this out a little better. Okay, so let's draw it. Let's go over here, right? So we'll start off with, I'm gonna draw it above, try draw it at a slant. Actually, that's terrible. Right, so this is what our diene, right? So now we have the dienophyte, right? So now if I drew it here, I think this would be an O acetate group. I'm going to abbreviate this as OAC, okay? And the reason why it makes it cis, right? As Mohammed there said, right, is if you look at any alkene, right? If you have two R groups, right? The other side is going to be H's or whatever, right? Whatever, if they're both on the same side, that's cis. If it's R and R like this, it's trans, right? So anyways, back to this product, right? I'm just going to abbreviate these group as OAC, right? So where the bonds kind of form, right, is essentially you're having this bond form and this bond form. Can you see the cyclohexane we formed here now? You see that cyclohexane, right? You could see that base structure now that's formed. It's between 1, 2, 3, 4, 5, and 6 carbon, right? Maybe, yeah, let me label them. I think that'll make it a little easier, right? So carbon 2 bonds to carbon 3, carbon 5 bonds to carbon 4, right? And that's gonna be the new bonds that formed. The bond between carbon 3 and 4, right? If we drew arrows here, right? This arrow would be like this arrow would be like this, right? So this carbon, the 3-4 carbon, the double bond is gone now because that's attacking, 5. And then this bond goes here, right? So now if I drew the new structure, right, and labeled them again. Oops, let's draw that a little better. God damn it, sorry. There we go, that's a little better, right? So if this was 1, 6, 5, what was this, 2, 3, and 4, right? So the new bond we created was between 2 and 3, right? Are we clear on that? That was this pink bond here, right? And then the other bond we created was between 5 and 4, right? Do we see that bond?
Clear. Yeah.
So then remember this double bond between 6 and 5, where is it going to be now? So this double bond here, where is that going?
I guess like well, you showed us going up with the arrows to 1 and 6.
Yes, so this is where that double bond is, right? So that's the only double bond you're going to get. The double bond between 3 and 4, is it still there or is it gone? It's gone, right? That's where this arrow right here is, right? That's the bond going, as I showed here earlier too, right? So essentially you're creating a new bond between 2 and 3, 5 and 4, and you're eliminating the double bond on that original dienophyte, right?
Oh yeah, I see it.
Yeah, so I'll do this for all the example. I'll just label the carbons because I feel like it's a lot easier when you label the carbons. Let me put this 3 and 4, right? And what was attached to 3 and 4? The OAC groups, right? And because they're on the same side, right, we expect them to be on the same direction. So in this case, we'll just put it on actually.
I'm sorry, I'm not like really familiar with the vocabulary because there's just so much. OAC stands for the double bond O and the OMe group.
Yeah. It's an O acetate group. I just abbreviated it.
Okay.
You know what? Just to not confuse you guys, I'll draw out the whole group. I just abbreviate things, and in general, you'll see people abbreviate things because we hate writing stuff out. But for simplicity's sake, I will just keep it aligned. So OMe, right? This is also on a thing, right? So this was, as we said, this was a cis alkene, right? So that's why both these groups are on the same side, right? So let's do another problem, right? So we could do the number system again. Okay. So here we have one. Let's use a different color for the numbers.
Sharuk,
Yeah, what's up?
I have a question here. For the first example you did,
Hmm.
I feel like there's an extra carbon. Don't know where is it coming from in the product. You see the O, the double bond O, oxygen.
Yeah.
So I know like the mechanism. I know how to draw the arrows, but I can't compare the product to the dienophile that you had before.
Okay. So if I was to make this all orange, right? So this is all orange, right? This is where the dienophile was, right? There's no extra carbon. You just created new bonds. You're not creating any new carbons in this reaction, right? So this was where the original dienophile is. Those arrows represent the new bonds we formed, right?
So what about the purple lines that you have in the product?
Those are just showing the new bonds we formed. That's still the product, right? If I wanted to, I could turn them all white just to help you guys visualize what those arrows did, right? That's what I was saying earlier. It was like I was going to draw these as colored, right? So that way you could see, you know, which specific bonds we created. We created this purple bond, and this purple bond, right?
Okay.
Yeah. So I'll just keep the numbering system because that might be a little bit easier to see. So we have 1, 2, 3, 4, and then we have 5 and 6 here, right? Now, whenever you see a dienophile kind of looking like this, first of all, is this cis or trans? Yeah. And as Nada said, rotate it, right? Is a cis or trans? So it's trans, right? If we were to draw out the hydrogens, you could see this even easier, right? Hydrogens are opposite sides. They're trans to each other. The two acetyl groups are on the opposite side, so they're trans to each other. So one thing we'll do is I'm going to rewrite this to rotate it so it's easier to get your product, right? So now if I drew this like this, oops, make it white. Oops, just give it a little bit more space. Oh, that should be on the other side. Okay, so that's the trans product now. We have 5 and 6, right? So the double bond, right? Once again, let's do the arrows, the mechanism. This double bond is going to come and attack carbon 5. The double bond between carbons 5 and 6 will come attack there. The double bonds between 3 and 4, right, will form a new double bond between 2 and 3. Now, if we draw out our new structure, right, the base is going to be a cyclohexane, right? Let's label all the carbons. 1, 2, sorry, we started here. This was 1, 2, 3, 4, right? And we'd say this was 5 and this was 6, right? So once again, hopefully this is a little clear now, right? We created a bond between carbons 1 and 5, and we created a bond between carbons 6 and 4, right? The double bond between the carbons 5 and 6 is now gone. And now there is a double bond, right? That moved from 3 to 4 to 2, 3, right? So that's the base structure, right? Now it's just the substituents that are left, right? So if
Wait,
you're having,
why'd you put 5 and 6 in that order? Does that matter, or can it be like flipped all the way around?
it could be flipped the other way around. Just keep the numbering system the same, right? I just happened to number it this way, right? So yeah, if you're having difficulty with it, just use the numbering system. That way you can track the bonds, right? Because I feel like the best way to, start getting this is just understanding that base cyclohexane you form, right? That 6-membered ring. It's a 4+2 addition. You always get a 6-membered ring. Then you just have to figure out where some substituents are, any additional rings, and the double bond, right? But if you get that 6-membered ring down, you'll always get it down. But if you're having difficulty, I've always found that for people who have a little bit more difficulty with it, use the numbering system so you can track the bonds you're creating and track the bonds you're destroying, right? Does the numbering system help? And like compared to just doing this, right? I think it's easier to track, but one thing I would say, once again, you got a time limit on your exam. So practice as much as you can now in between your exam. You're not gonna, you gotta time manage on your exam. Anyways, so 5 and 6 have 2 substituents, right? So we could draw them as such, right? Like this. Like that, right? Now, the thing is, right, this could have gone both directions, right? If we flipped this dienophile, right, like up and down, the group on top could have been on a wedge and the group on the bottom could have been on a dash, right? And because they're not on the same side, right? Because they're on the opposite side, this wouldn't be a meso product, right? Because in space, they would be above and below the plane of symmetry, right? So do we have an enantiomer here, or is this the only product? You have an enantiomer, right? So I'm going to draw out the enantiomer. You could write plus En, but just to show you how the other enantiomer would look, right? It would look like this. No, you don't. You could write plus En plus enantiomer. All of that stuff is fine. I just want to, for those who might be having a little difficulty visualizing, I'm drawing both. So technically you have both enantiomers, and hopefully now you can see why, because this one, it's on a wedge and this one's on a dash. So this would be like R, this would be S, this would be S, and this would be R, right? Yes. So like if you form enantiomers, right? If you're like going for the major product in this question, if you form a racemic mixture, you have to indicate that, right? So you could write plus En, or you could write that it's racemic, right? But if you are forming something that's a racemic mixture, you have to indicate that, because what a racemic mixture, by definition, there's nothing is, they're 50-50, right? So you won't have one over the other. So when the dienophile is trans, we have enantiomers. Yes, for the most part. Just trying to think of any cases where that might not be true. Yeah, so when the dienophile is trans, yeah, for the most part, you'll always have enantiomers. And when it's also unsymmetrical, you'll also have an enantiomer. Yeah, for the most part, yeah, as far as I can think. I can't really think of any cases where that wouldn't be the case. Because the groups would be on different sides, right? So, yeah. Okay, last one. Once again, let's flip this. CN, CN. So what if the trans sub were different? Which would be, oh, that's a good question. So yeah, if it's unsymmetrical, then they wouldn't be enantiomers. Then they would be 2 different products, right? And they you would have to draw both products, right? Because you can't just indicate one's the enantiomer over the other. Well, actually, let me see. If you have, sorry, let me just quickly do this. So if you had something like CN, like, I don't know, if you had an acetate group here. Oh, this would be cis though. If you had trans, so I'm just quickly doing this. And then you'd have the opposite. I guess they would be enantiomers. I have to double check that. So you could probably indicate it. Yeah, they should be enantiomers too, even if the groups are different. Yeah, I'll have to double check that in chem. So I'm just gonna make a star note of that. Anyways, this is the last example. So this one is with an alkyne, right? So it doesn't, the dienophile doesn't just have to be an alkene. Right? This is why I wanted to show this example, right? Remember, by definition, this is a 4+2 cycloaddition. 4 electrons from diene, 2 from the dienophile, right? So once again, let's do the labeling. 1, 2, 3, 4. We'll call this end of the alkene 5, this end of the alkene 6, right? Draw our bonds, attach this end. Only one bond from the triple bond, right? Remember, this has 2 pi bonds, but this is a 4+2 cycloaddition. We only take 2 electrons from the dienophile, right? So only one bond is going to come and attack here, and 4, right? So now we will actually have a product that has 2 alkenes in it, as you guys will see. So if we label this 1, 2, 3, 4, this is 5. Oh, let's put it inside. 5 and 6, right? So 1 and 5 was the new bond we created. Makes sense. 6 and 4 was the new bond we created. So makes
Can you just
sense.
flip the 5 and 6? Because it's confusing when you do it like that.
What do you mean?
Like, you know how it's 1, 2, 3, 4, and then you have 6 and 5.
Oh, okay. Yeah. Now I understand what you meant. It's just I go from top bottom. So like I said, as long as you keep the numberings the same, it doesn't really matter. So yeah, we'll call this 5 and 6 to make this a little easier. So now what's not shown here, right, is why is my eraser not working? Yep. So we have a double bond between here, right? We have those 2 new bonds between 1 and 6, and 4 and 5, right? And then remember, we only took 1 pi bond, right? So when you're doing a Diels-Alder with an alkyne, right, you will have a double bond left over. So let's draw this a little better. A second. Right, and this was 5 and 6, right? And then the substituents, right? There's no stereochemistry here. So make sure, like, in case this comes up on your exam with an alkyne, right? I don't know if you'll lose points or not, but there's a reason they're drawn planar, right? This is an sp2 hybridized carbon, right? It's trigonal planar, right? You don't draw a wedge or a dash if you have an alkene still between your dienophile left, right? So when it's an alkyne, right, there's no stereochemistry on the substituents, right? They're all flat, right? Just be aware of that, right? Because I've seen a lot of people on exams that I've graded in the past, they'll draw the wedge dash, and that means you don't understand the kind of geometry of those positions, right? So it's all planar, right?
Wait, so only alkenes have the wedge dashes?
Yes. So when your dienophile is an alkene, your final product, right, between carbons 5 and 6, right, is going to be sp3 hybridized, right? But when your dienophile is an alkyne, right, there's still 1 pi bond left over. So you're still an alkene there, which means it's sp2 hybridized and everything is planar. So you don't have to worry about stereochemistry at all when you're doing alkynes, right?
Okay, thank you.
Yeah. Okay. Well, yeah, it has to do with that at that point in the molecule, like if this was a plane, right? Remember this is alkene, everything is flat in the plane in an alkene, right? It's all along the plane. When you have something that's tetrahedral, right? Things are coming out, above the plane, right? So everything's flat along with each other. So there's no really, the only kind of stereochemistry you could have is like cis-trans stereochemistry or EZ, right? But in the case of Diels-Alder, since you're a locked-in product, right, it's only going to be pushing off one way. The angles are 120 degrees, right? And also here, if you look at the alkyne, right, there is no stereochemistry to begin with. It's all linear, right? So when you do a 4+2 addition on it, kind of makes sense. There's no stereochemistry in the final product. Okay, let's see. I want to get examples of I'm not sure. It's going to be close to exam time. Our exam is 10:05. So what is that? It's like 2 weeks. So either the Monday night before sometime or that Saturday before, one of those days. So I'll let you guys know the week of. Okay. I need to do products that have, there we go, cyclic, the bicyclics, right? Okay, so cyclopentadiene, or if you used furan, right? You have all sorts of different stuff. So let's do both 16.17. We're gonna do really, we don't have just the bicyclics left here. And then the last one is the regioselectivity, which I want to spend a good amount of time on. And that more or less covers all the cases for Diels-Alders. And we're gonna probably end it here. So 16.17 is the bicyclic stuff. So this is important, right? Because there's something called the endo preference, right? Which we'll talk about here. So here we have this molecule, which you'll probably see a bunch. I probably have seen a bunch now. You'll probably see some more of it in the next chapter. This is called cyclopentadiene, right? Cyclo, it's a pentane ring, diene, right? It's actually more commonly used than the, what is it? 1,3-butadiene, because it's locked into the S-cis formation. Oh yeah, one thing I kind of briefly forgot. Everything here is what's called S-cis, right? Your alkene has to be in this S-cis. So if you have something that's S-trans, right, where the alkenes, right, the single bond between them, right, this is called S-trans configuration. This is called S-cis, right? For Diels-Alders to work, your diene has to be S-cis, right? So in the case of all these 1,3-butadienes, they're all shown in the S-cis formation. And if you're not shown that on your exam, you have to convert it to that, right? To make sure you're doing it properly, right? In the case of cyclopentadiene, it's locked into an S-cis.
Can you give a quick example of how to like change it? Do you just draw it
Just
as
rotate it. So like if you just had this, right? You can literally just do a rotation, right? Now they're both on the same side.
oh, just turn it into the
Yeah.
S-cis.
Yeah, so the double bonds are on the same side. So the S-cis refers to, I guess technically that S, like this is a S bond, I guess, between the two dienes, right? And the cis means the double bonds are on the same side. S-trans means the double bonds are on the opposite side, right? Okay, so what do we have here? Oh, sorry. Okay, so we have our diene. It's locked into S-cis. We have our dienophylle. It has a nice electron withdrawing groups on it, right? Whenever it's done converting to, what's it called? Give me a second. Okay. All right. So now, once again, let's label our carbons. We'll call this 1, 2, 3, 4. We'll call this one 5, right? And we'll call this 6 and 7, right? Once again, the bonding things works the same way. The final product is going to be a bicyclic product, right? So you have this tax here, this double bond attacks there and this attacks here, right? So now if you look at where carbon 5 is, if remember the base for all these products are that cyclohexane, that means there's a ring coming above it, right? And that's why you're going to get bicyclic. So when you have cyclic dienes, right, you're always going to get a bicyclic product, right? So let's draw out our base. So now we're going to draw it in 3D. You could technically draw it in 2D. I just would not suggest to, because it's a lot easier to, it's easier to mess it up in the 2D version, right? So bicyclics, as you guys probably remember from Orgo 1, is one of the few things you want to draw shown in 3D space, right? So I'm just going to draw the base for it. And I'm going to start labeling carbons right now. So this is 1, 2, 3, and 4, right? Those are the original 4 carbons. This was 6 and 7. And remember, 5 is between 4 and 1. So that's another ring. That's a one-membered ring above. So it looks like, whoops, just draw that a little better. Right? So this would be carbon 5. Right? So 1, 2, 3, 4, 5. And if you look at it, right, if I kind of drew this cyclopentadiene like this, maybe it's better to see. This is kind of where that portion of the molecule comes, right? You kind of bend it upwards and you'll see that original thing is still there, right? The bonds we formed were between 1 and 7 and 4 and 6, right? As you see here, the new double bond is between 2 and 3. So let's draw that in as well. And now for the substituents, right? So the substituents, right? When you have bicyclic, right? Essentially, there's something called the endo preference, right? So this is kind of nomenclature for bicyclic molecules, is you have exo or endo, right? It's not just limited to Diels-Alder. It's just the way chemists like kind of describe where the substituents are in space, right? So you could have things that are exo, which are pushing up this way, and then things that are endo, which will be pushing down this way, right? Try to draw this one a little better, like that, right? So now for Diels-Alder, there's an endo preference, right? So the endo preference essentially has to do with the transition state that this goes through, right? Basically, what happens is when this is all forming its new bonds, right? They're forming your new bond here. Right, you're going to see that the electron withdrawing groups on the dienophile, right, they're going to align closer to this kind of cyclic transition state that's being formed. I think the book has a much better diagram that I could show, right? So those interactions, right, those pi-pi bond interactions, which I will draw with this red, like, right, between, like, in this case, it would be the nitrile groups, right? They're a lot better when it's going endo. So the transition state is much lower energy for the endo pathway, right? But the final product, endo, is higher in energy in exo, right? Because if you look at it, right, if things are at the exo positions, like pointing up this way, this whole thing is less sterically hindered, right? Because things are farthest apart from each other, right? But the reason why the endo product is preferred, right, is because of that transition state. Now that is, he probably mentioned that in lecture, both probably Bozon and Biscoe, right? And it's also shown in your textbook, the whole endo preference rule, or the endo rule, whatever you want to call it. And the same thing about the transition state and the final product is shown there as well. I'm actually literally looking at the diagram right there. But I just wanted to show that transition state to show you why the endo is preferred, even though it's higher in energy, right? So whenever you're doing the cyclic Diels-Alder, where your diene is cyclic, always it's endo preference, right? So in this case, both our CNs, let me just draw this all in white, are going to be downwards, right? So this is the endo product, right? This will be the major product that we get when we have a bicyclic molecule form. So when the dienophiles is trans, right, then you can't really, you can't prefer the endo over the exo, right? So then you'll get a mix, right? So one side, thing's gonna be up, one side's gonna be down, and you'll have the enantiomer as well, right? No, it's not a wedge. It's just going down. So let me try to draw this as a line. Technically, if you want to make it very clear, that's what you draw. You could write the hydrogens here. I just generally only draw the substituents, right? It's up to you, right? But just make sure it's pointing downwards, right? That's the key, right? Don't make it point upwards. That's exo, right? So this is an endo product or endo adduct, however you want to call it. Let's do another example. We'll do a few more. So someone has asked the trans. That's the next question I was going to do. Is with trans. So this here is this molecule here is called furan, right? If you don't want to know, we are using a now trans dienophile, right? So let's label carbons or atoms. 1, 2, 3, 4, right? And because someone was having the issues with the numbers, I'll label these 5 and 6. We'll call this 7, right? So what is it? 1 bonds to 6, the bond between 1 and 2, the bond between 5 and 6 bonds to 4, and you form a new bond between 2 and 3, right? So now let's draw our base cyclic structure, right? We have, let's label these 1, 2, 3, 4.
Can you make the part where the oxygen is 5 and make the other numbers?
Okay.
Yeah.
Okay. And what we did was 6 and 7. Okay, so we'll do that. 6 and 7. And then we said oxygen was 5, which is between 1 and 4. So it's pushing up, right? Just make sure you draw the oxygen there, right? And then just for clarity's sake, that is 5, right? So that we got our base structure. We're missing our double bond, which is here, right? And now, as someone said, what if you have trans? Well, now you're going to have a mixture of products, right? So on one side, right, you can't have complete endo preference here because the way the dienophile is, right, one is always going to be up, one is always going to be bottom, right? So what basically the endo preference, right, when you have both things endo is for only cis, right? Then you make sure both things are endo. But when you have a trans dienophile, right, one thing has to be up and one thing has to be down no matter what. So in this case, we can draw one CN in the exo position and the other CN in the endo position. And also technically the enantiomer exists, right? No, because you have an enantiomer as well, right? Because if we drew the other product, you'll see like the CN would be exo on this carbon on carbon 6, and the CN would be endo on carbon 7, right? And that would just be the enantiomer of this entire structure, right? So the other structure is just the enantiomer, right? Okay, let's do another one. Let's do okay. CN on 7, it's exo. So we don't call it axial or equatorial here. We call it exo or endo, right? So it's pointing up. So technically, I guess that's like similar to axial on cyclohexanes, right? But the correct, I guess, nomenclature is exo and endo in this case. So yeah, it's pointing upwards like that, and the other one's pointing downwards. Okay, let's do one more here, and then I want to end off on regioselectivity, which is I feel like people have the most trouble with. So all of these, if you noticed, right, for the most part, they're symmetrical. We have both symmetrical dienes and symmetrical dienophiles, right? You could run a line of symmetry between all of these. And even if like one is non-symmetrical and the other is symmetrical, it doesn't, it won't affect the product, like how it like aligns with each other. So in this case, you'll see that only our diene is symmetrical, and we have an unsymmetrical dienophile, right? But it won't affect the outcome of the product, or like where the product reacts with each other, right? But when both are unsymmetrical, right, then it's regioselectivity is important, right? So here, right, one is still symmetrical, so regioselectivity is still not important, right? So let's go around naming them. 1, 2, 3, 4, and 5. This was 6. This is 7, right? Now to make this very clear, right? This is an H here, this is an H here, and this is an H here, right? I'm going to show this on the final product to make this clear, right? So this point, hopefully we have the mechanism down, right? This goes here, here, and here, right? We are drawing our product now. Carbon. So now let's label this, right? So this was 1, 2, 3, 4. This is 5, right? And then we said this is 6 and this is 7, right? Here, technically, we have, this would be an E alkene, right? Actually, no, you could still call this trans because the hydrogens are trans to each other. So it's E or trans is fine, right? So once again, in this case, right, it doesn't matter which side you choose. Let's draw it downwards. So hopefully, oh, sorry, use the white color. Hopefully it's not completely straight, but it's fine. Should be that, right? And then technically this is an H, right? And you could have this the other way where this aldehyde group could have been on the exo position, right? So that product would be the enantiomer, right? So you could draw either one, just write plus En, right? So in this case, it didn't matter if you drew it endo. I would always prefer to draw the larger group endo, right? But the enantiomer would also technically exist for this case, right? So do these questions right here. What is it? Let me just look over them. These are very good questions. 16.17 and the other one was 16.13 for as much practice for the products of Diels-Alders. And now the last question, which we're going to end on, is regioselectivity. And then next week we will do MO stuff and all that. So they are both on 7. Yeah, so they're both on 7. The hydrogen is exo. Technically, I could have drawn it like this, and it would still be fine. If I drew it like this.
Sharuk?
Yeah, what's up?
This might be a lot to ask, but
Mhm.
our exam is coming up. Is it possible you can also like spare another day other than Saturday to like go over like exams with us?
That's what someone was asking earlier. I generally tend to do one review session before the exam, so I'll figure that out the week of the exam.
Oh.
But
Sure.
other than
That is
that,
not going to be enough. It's just
yeah,
so
well, you know, I'm gonna do an extra review session, and then like I said, when I am available, I'll let you guys know in the chat if you wanna ask questions in campus or whatever. But like, you know, I have a lot on my plate in terms of our research this semester.
Yeah.
So, you know, everyone's got different schedules. So I'm trying to, you know, as much as I can, but you know, you're gonna have to do a little on your own as well.
Yeah, I understand.
Yeah, what's up?
So even if you can't spare another day, that's absolutely fine. But if you can, like, do it on a Saturday, like regular restation time, on the 2nd, for example, where you can spend like 2.5 hours with us, regular restation time, and do the exams then. That's going to be better than doing it the night before, because Monday is a work day or class day for most of us, and doing it the night before, it's not going to give us time to look at it. So just do it regular recitation time, but give us like time before the exam date,
Like I said, around that time, I'll figure it out. It's all dependent on what I'm working on that week in the lab. Well, like I said, we'll figure something out. We still have like a little over a week before we decide. Okay, let's do the final question, which is when you have an unsymmetrical diene and unsymmetrical dienophile, right? So this is 16.18, right? So before I do this, I think I should have it from a previous semester, but let me just see. I had these nice rules here. There you go. Just gonna copy and paste these. Where's give me a second. I need to. Try to grab this all perfectly. Okay, let's paste this down here. Or do this. Yeah. Okay, so when you have unsymmetrical dienes and dienophiles, right, then the positioning is kind of important, right? So here I have examples, right? So unsymmetrical dienes, right? When you have an electron donating group, right? Let's say on one side of it, right? Remember, this is an electron donating group. So if you think about the arrows, right, it will donate electron density, right? Well, like here, this will push here, right? And essentially, it'll make the carbon opposite of it partially negative, right? If we were to draw a resonance structure out, right? Like, so if this was like an OH group, you take one set of electrons, you push it in, you'll see basically the carbon on the opposite end is going to have a negative charge in the resonance structure. So essentially, we could say that carbon is more partially negative, right? Same thing happens if it's on the opposite side, right? So when the electron donating groups, we'll get to this in examples, right? When they're on the terminal positions of a diene, right? The opposite carbon is going to be more electron rich. So you could donate that as, or note it as partially negative, right? Now, when you have the internal electron donating group, right? So let's say this had a pair of electrons, right? And it donated here, right? Then it's going to push the electrons, right? This is a double bond, so they will push it on the carbon at the same side of it, right? So when it's on like this internal position, an electron donating group like OMe, OH, or, you know, OR groups, whatever groups they might be, right? The carbon that's next to it will be partially negative, right? And you could draw out the resonance structure to show this. I'm just kind of quickly showing you why this is partially negative, right? And I'll show you better in the example. But this is just kind of like the general structures you could draw out, right? Same thing if it's on like this position here, right? The carbon next to it is going to be more electron rich, right? And then for the dienophile, it's very simple. It's just the carbon that when it's unsymmetrical, it's the opposite carbon is going to be electron poor, right? Because this is an electron withdrawing group, right? It's pulling away electron density, right? So these are terms you're going to see in the next few chapters, but electron donating group is something that donates electron density. Electron withdrawing group is something that withdraws it, right? We're going to become a lot more comfortable with this in chapter 17 and 18, but this is usually the first time I introduce it. He did do it perfect. Okay. I'm so glad he already introduced those. So if this was like, let's say a carbonyl, like I showed earlier, right? It's pulling the electron density towards it, which would make this carbon partially positive. If it's on the bottom like this, same thing, right? So let's do an example of this to show what I mean. So this is 16.18, right? So this is, oh, whoops, drew that wrong. This is OMe, right? And we have, let's draw it the other way just to make it clear. EHO, right? So first the diene, right? It's unsymmetrical, right? It only has an OMe on one side, right? So we have to see which side is more partially positive. So now let me show you the full resonance structure to maybe make it more clear what I was doing, right? Was if I drew this down here, right? OMe like this. If he already did this, and hopefully you guys have seen this, right? But if I drew a resonance structure, push this here, push this here, and push this here, right? We have a resonance structure that looks like this would be positive, right? So essentially that carbon, right, is going to act as a carbanion, right? So we could basically say when you see an, and that's why I said if you kind of memorize these base structure where the electron donating group is, like in the top here, right? It's over here, so we expect this carbon, right? I'm gonna actually use orange, so it's not the same color as below, right? This carbon here, we could say is partially negative carbon, right? Now CHO, right? Non-abbreviated, right? It just looks like this, right? That's CHO. Right? You should also just know the group right now. It's a simple aldehyde group, right? So if you see CHO, you think of an electron withdrawing group, right? These bonds are conjugated with each other, right? They're one carbon apart. So if we were to draw resonance structures, right, they would look like here, push here. Then you would see that that carbon, right, is partially positive, right? Because in the resonance structure, there's a carbocation there, right? So we could write this as a partially positive carbon, right? So when you have unsymmetrical dienes and unsymmetrical dienophiles, the major product, right, is going to be based off the regiochemistry, right? Essentially that they have to line up a certain way, right? Because that's going to be the most dominant product, right? So in this case, we have to flip the second one, right? So if we flip this, right? So now we flip this, right? Now the partially negative is lined up with the partially positive side. And that's going to be the, he did these. Okay, so I'm glad everyone has an understanding. But I just wanted to make sure I went over that top part. But you could kind of memorize that top part. So you always know which side is partially negative and which side is partially positive. Right now we could just go ahead and do our product. So our major product is when the partially negative and partially positive is lined up with each other. Right? So just write that.
I'm sorry. I got kind of lost. Didn't you, wasn't the second structure like a double bond with like a CHO attached to it? Where did this?
Yeah, so this is the CHO group, right? So if I just abbreviated it, that's CHO, right?
Oh, okay.
Yeah, no worries. So this is CHO, right? That group. I just wanted to show below why it was doing that. But if he already went over it, then I'm kind of glad he did that. So now we could line these up, right? So I'm just going to abbreviate this here just to indicate this is partially positive. Right? And now we can get our product, right? Boom, boom. Okay, I'm not going to use numbers now. Like I said, if you want to practice with those, but you're going to have to start making sure you can do these at a reasonable pace, right? So we have an OMe group here. Sorry, we have a double bond here, right? We're going to have the OMe group here, right? And then we will have a CHO group here. That's the final product. Technically, yeah, they might be on the same side or possibly opposite sides, but stereochemistry is probably not too important here, right? The main thing you're probably looking for is the outcome of product. So generally, right, when things are below, like this answer is perfectly fine if you did it planar, right? But technically, the answer would probably look like, if you want it more detailed, OMe group would be this. I can't really determine whether the CHO would be on a wedge or dash, but I know for a fact the OMe would be on a dash, right? Because it's kicking on the outside. But this planar answer should be fine. I don't think they're gonna knock you out for not showing the stereochemistry. Usually they never ask for stereochemistry because it's more to whether you understand, you know, what side of what part of the diene and dienophile is more reactive. So let's do like 2 more examples on this and then we'll end here. So we'll do B and C. Yeah, I guess technically it would be down. The main reason I wasn't sure, it wouldn't be sure if it's down is because then it would be on the same side as the OME, right? But, and then there would be like repulsion effects. But shouldn't make too big of a difference, I guess. That's why maybe in the major product, you'd have this on a wedge. So that way you have that substitution, right? That, like I said, the main, I know for a fact the OME is going to be on a dash. I can't really speak about the CHO. Okay, so let's do B. So we have this. MEO and CN, right? So here, A or B, which is going to be more partially negative. I'll mention that once we do this. A or B, so we have B there, right? So good. So B, right, it's on the same side as if you look at that general structures I drew above there, right? Same side, right? This is partially negative, we'll just write here. And then what about on CN, A or B, which is gonna be partially positive? B again, right? This is partially positive. So nada, what I was saying about aligning the charges, right? The partially negative charge is going to be the carbon that's bonding to the partially positive charge, right? So this is that bond we're creating, right? Is between these two carbons, right? That's going to be the major product, right? Technically, this could go both ways, but the major product will be when the carbon with the negative charge and the carbon with the partial positive charge are aligned to each other, right? So now if we did this arrows, right? This bond goes here. See, technically we should draw it this other way. It doesn't matter, but this bond goes here and then this bond goes there, right? So that partially negative carbon is lining up with the partially positive carbon, right? And our final product here, right? Will look like cyclohexene. There's no stereochemistry here. Yeah. Well, what's up?
I'm sorry, but I get like the partial negative and positive bonding together, but like why are the arrows like going counterclockwise now?
It doesn't matter. Like for all those examples below, I could have like here, like let's see. It wouldn't matter which way I did the arrows, right? You're still gonna get the same thing, right?
Okay, can you be consistent with them? Because it confuses me when you switch things around.
In that case, I had to do it that way. But like I said, it doesn't matter which way you do the arrows, right?
So I can do the arrows the clockwise direction.
Yeah. So you could do them clockwise. Just make sure the bonding is correct, right? So whether you did it clockwise or counterclockwise with them. In this case, they happen to go counterclockwise, I guess, right? But in the other cases, I just happen to do it that way because I naturally do it that way, right?
And you did it this way because you just felt like it.
No, it's because technically, right, the electrons are coming from the partially negative portion. That's why I did it. I mean, it wouldn't be wrong if I did it the other way. It's just that logically it makes sense. This partial negative area is where electrons come from, right? And any arrow represents electron movement. That's why I just did it that way.
Okay.
Yeah.
Right.
So, I mean, if anything, I could have just flipped this up, right? I could have done it like this, and then you'd see the arrows are the other way. So if I did it like, what is it? MEO, right? And then I did this CHO like this. Or is it CHO or CN, right? Then the arrows would go the way we were normally doing it, right? It would just be this, be this, be this. It just happened to be that it was arranged that way, right? But the arrow movement is still the same, whether you go one direction or the other, right? Okay, so MEO here has no stereochemistry, and then the CN is technically, I guess, undefined stereochemistry. Probably like someone was saying, probably down as well. But like I said, you can't really say whether up or down will be more. I mean, all they would be was enantiomers to each other anyways. He said it would be down. Okay, if that's what he said, okay, then I will specifically write that. Outside groups. Yeah, so that's yeah, so like if you have outside inside here, right? So this is technically inside, this is on a wedge, right? That's why I knew the other one here was gonna be on a wedge. I mean on a dash because it's the outside group. So yeah, we could put it on the dash, but I think planar will be fine as well, because technically well, I don't know. Professor Bisco definitely knows better than me. So listen to what he said. I think it will be fine if it's on a line. Generally, like I know Andy and Boson are fine with it on a line, but like I know Professor Bisco is very knowledgeable too. So if he said it's gonna be on a dash, then he's probably right. So you could ask him though if it's fine if you don't show the stereochemistry, right? Because I think the more important thing is the regiochemistry of the products, right? That which way they're aligning to each other, right? So just do one last example, right? Where there is no stereochemistry for sure, right? Would be with that. Yeah.
Could you go up and need to take a picture of the rules you said, not the rules, the ones you said we have to memorize? Could you kind of do this quickly?
Yeah, let me just finish the example and then I'll just do that.
Okay.
So we have one last one. So there's definitely gonna be no stereochemistry in this one. But that's good to know it's gonna be down. I actually did not know that. Because I just figured you wouldn't be able to differentiate. I only knew for the dienes because those are the, like as you mentioned, outside, inside. I didn't know for the dienophiles. See, the more you learn though. Okay, so here, right, once again, let's call this A and B. Which one is going to be partially negative? So if we were to push the electrons, right, the electrons push here, the double bond is on the same side. It would go here, be A, right? No worries. That's why you're here to practice and get better. So partially positive side, we expect on, partially negative side, we expect on the same side as that electron donating group, right? I think this should be pretty obvious that this carbon is going to be the one that's partially positive here, right? Because it's on the opposite side of the CO2 ET group. That group looks like this, in case you guys want to visualize, right? It's a carbonyl, it's an electron withdrawing, right? So the partially positive carbon's there. So now we can just go ahead and flip this, right?
The first structure, it can either be A or B, right?
No, it's only A, right? Because the electron donating group is on that side. So if you do the
Oh, okay, I
resonance,
see
you'll
now.
see. Yeah. I was just writing A or B to people can pick out. Okay, so I'm gonna flip this structure. It's probably not gonna flip properly because of the text. Yeah, it's not too bad, I guess. Surprisingly, that ENT still came out fine. CO2T, right? So now this lines up this way, right? And have our bonding, right, this way. One bond, right? This is an alkyne, so there's one bond. There's gonna be definitely no stereochemistry at all in this molecule.
The right side is supposed to be positive, right?
Yeah, so let me just write that there again. Partially positive, right? So partially negative lines up with partially positive. So our final product will have no stereochemistry since we have two alkenes that form, right? So there's alkene here and here. So on this side, we have ETO, and we said the, CO2 ET here, right? Okay, Drona, you asked for that thing above, so we're gonna end there. So these questions for Diels-Alders are, oh shoot, I forgot. My bad, let me redraw that actually. Thank you for pointing that, I forgot we were doing cyclopentadiene. Oops. So the structure, my bad, ignore the structure, guys. Should look like this then. Second, make sure I do this correctly. Should be flat, right? So notice I'm not really going up or down. I'm just kind of extending it as being flat here. And this should be TO. This is also flat. ETO. Sorry, ignore that structure up there. Sorry about that, guys. Thank you for pointing that out. Nada. But yeah, just if you had a bicyclic where the things are flat, right, where you have an alkyne or whatever, right, just make sure you don't draw it endo or exo. Just draw it in plane with that alkene there, right? So that should be the final product. Okay, so yeah, we'll end there. So these questions right here, 16.18, right, 16.18, 16.17, 16. What is this? 5, I guess. No, 16.13, 17, and 18. There's still more to do practice in there. Here you go, Madrona, for your picture. Let me just check the end of the chapter. I think he probably mentioned the questions that you need to do, but end of the chapter probably has way more questions as well. So yeah, 16.42, 43. So tons of Diels-Alder practice here, right? But hopefully that covers all kind of examples you will relate to Diels-Alder in this case. Anyways, enjoy the rest of your weekends. And yeah, have a good week. I'll probably see you all next week.
Thank you, Sharu.
Yep, no problem.